Good morning, everyone. Today is the last class for this course. Yeah, happy, am I right? Yeah, we have already had the 5 weeks classes and so many things I know. Yeah, but every class has the most important thing. Yeah, so you just focus on the most important thing, and then I think you will find it's not that difficult for you. And if you have any question, just let me know. Yeah, last class we talk about EM induction, and which means if uh, mm, the magnetic things and the electric things they interact with each other, and there will have some uh, have some results such as induced current and induced voltage. For the induced voltage, we call it motional EMF. And then for the induced current, we can we know how to calculate that, and we know how to find the direction for that in last class. Yeah, in a word, we mainly focus on EM induction in last class. Yeah, today we will talk more about EM induction, and also we will talk about EM waves. Yeah, because you can see electromagnetic it's kind of it has a wave features. Yeah, we will talk about in this class. Okay, let me share my screen. Yeah, in today's class, we will continue to talk about EM induction and EM waves. And last class we mainly focus on induction, and today we will focus on EM induction and EM waves. Yeah, we will talk about more about EM induction and EM waves. Okay. Yeah, this is this chapter's goal, to understand the nature of electromagnetic induction and electromagnetic waves. Yeah, this electromagnetic is just a EM. Yeah, this is a full name and this is a short name. Yeah, and let's let's check today's goal. Firstly, we will review EM induction, what we talked about in last class, motional EMF and induced current, and how this induced current velocity come out, and how these things happen, and because of what? Do you remember that? Yeah, it is magnetic flux. Am I right? Because after if a magnetic flux changed, and there will have some induced current and induced voltage. Does make sense to you? Yeah, and after that we will explore Faraday's law. And then we will study electromagnetic waves. Yeah, and you know, electromagnetic has some a wave feature. Yeah, we will talk about that. And finally, we will learn the photon model of electromagnetic waves. Yeah, this is what we will talk in today's class. Okay, let's continue. Yeah. Let's review what we talk about in last class. Yeah, we talk about the motional EMF. Actually, the motional EMF is just when the conductor moves in a magnetic field, and then there will be the you can see here. This is a conductor, and when it moves in a field, and then for example the field, and then the positive charge will go up, negative will go down, and then there will be a potential difference. Yeah, we talk of we named this like a motional EMF. Yeah, the motional EMF of a conductor of length, if this conductor length is L, and moving with velocity v, and perpendicular to a magnetic field B. Yeah, And then this we can calculate the motional EMF using this equation. And this is EMF due to the motion of conductor. This is velocity. This is length, and this is magnetic field strength. Yeah, that makes sense to you. Yeah, just review. Call back what we talked about in last class. Yeah, and then we talk about something about the electromagnetic induction. Yeah, like I just talk about yeah the why the induced current come out. Yeah, like happens. Yeah, because the magnetic flux changes. Yeah, the magnetic flux measures the amount of magnetic field passing through a surface. Yeah, so this is the equation for the magnetic flux. And here, this is a loop. This is a loop, and A is the area of this loop. Yeah, and B is the magnetic field, and the theta is the x of this loop, and the angle between x of the loop and the magnetic field. Yeah, this is the cosine, this is the theta, and when the like a loop, this loop is just like the cosine theta equal. You can see if it is if it is in this direction, which means the theta is what? The theta is 0. Am I right? So which means there is no magnetic flux. But if it is just runs like this, which means this is a magnetic flux. Um, and this is the x of the loop, and this is the cosine. This theta is 90 degree. Yeah. This means this is a 19 degree, cosine 19 degree, which means it is 0. Am I right? So which means in this situation, the magnetic flux is 0. But in this situation, yeah, cosine theta is 0. Cosine 0 equal 1. Am I right? So which means in this situation, it is the biggest. Yeah. Sorry, I think I just redraw it, make it clear. Yeah, if you if it is runs like this, yeah, if then this is the action of the loop, and this is also the magnetic field direction, which means the theta will be 0. Am I right? Yeah, theta equals 0, cosine 0, which means 1. Am I right? So which means this is the maximum. The magnetic flux is the maximum. But if it is in this direction and the the theta equal 19 degree, which means this one is 0. Am I right? So which means the magnetic flux is 0. Yeah, so that makes sense to you. Yeah, I just review what we talked about in next class. Yeah, this means like as the theta increase, yeah, and the magnetic flux will decrease, yeah, because only when it is 0 and it will be 1. Otherwise, it will be smaller than 1. Does make sense to you? Okay, let's continue. And then we talk about the Lenz's law. Actually, the Lenz's law is for like finding the direction of current, induced current. And the Lenz's law like specifies that there is an induced current in a closed conducting loop if the magnetic flux through the loop is changing. Yeah, the direction of the induced current is such that the induced magnetic field opposes the change in flux. Yeah, which means if this one, if this bar magnet goes into this loop, which means the loop will generate a opposite like a electric field. So the direction will this one, and then you use you use the right hand rule, and you will find the current direction is this one. And if we go up, which means it will leave, and the magnetic field become smaller, and it will it will generate a same direction, and just like this. And then you will also use like a magnetic right hand rule. You will find the current direction is that's like clockwise. Yeah, that makes sense to you. Yeah, this is Lenz's law. Yeah, and let's continue to talk about today's class. And firstly, let's talk about Faraday's law. And an induced EMF, yeah, we use this symbol to represent induced EMF, is the EMF associated with a changing magnetic flux. Yeah, because if like the induced EMF is just like after the magnetic flux changing, there will be a induced EMF, and then we can use this equation to calculate the use Ohm's law to calculate the induced current, because usually we know the R. Yeah, that makes sense to you. The direction of the current is determined by Lenz's law. Yeah, we have already talk about that. And the size of the induced EMF is determined by Faraday's law. Yeah, like how can we calculate the induced EMF? Then we can use Faraday's law to like get the induced EMF. And then let's talk about Faraday's law. Yeah, Faraday's law is a basic law of electromagnetic induction. It says that the magnitude of the induced EMF, sorry, it should be this should be closed, is the rate of change of the magnetic flux through the loop. Yeah, this is the content for the Faraday's law. Yeah, and EMF, this one is induced in a conducting loop if the magnetic flux through the loop changes. Yeah, like I said, if the magnetic flux through the loop changes, and there will be an induced EMF come out, came out, and also the induced current. Yeah, if the flux changed by delta, this one, during the time interval, this one, and the magnitude of the EMF equals this one. Yeah, it's just like a the like a the magnetic flux change in a unit time. Yeah, this is EMF, like a motional EMF, like a induced EMF. And the direction of the EMF is such as to drive an induced current in the direction given by Lenz's law. Yeah, it's just the same with like the current. Yeah, because yeah, we will talk about later. Yeah, and you also can check this video to see Faraday's law. But you know, like the first law meaning talk about the induced EMF and the magnitude of the induced EMF. We can got using this equation. Yeah, it is like the flux, magnetic flux change in during time interval. Yeah, we can get the induced EMF, and the direction of the EMF is such as to drive induce current in the direction given by Lenz's law. Yeah, okay, let's continue. A coil consisting of n turns acts like n batteries in series. So the induced EMF in the coil is just this equation. Like this is just a per coil. The magnetic flux changed for in per coil, and this is like how in the time interval. Like this is in this time interval, like the magnetic flux change for per coil, and this is just how many like coil. Okay, this is for the like a coil well existing of interns. Yeah, and then we can get the magnetic induced EMF using this equation. Yeah, you can also check this video like for some applications. Yeah, let's I will now play those videos here, and you can play them by yourself. Okay, let's continue to talk about Faraday's laws. Yeah, there are two fundamentally different ways to change the magnetic flux through a conducting loop. Yeah, you can see there are two fundamental different ways. Yeah, to change because only the magnetic flux changing can generate the induced EMF, induce current. Yeah, but how can the magnetic flux change? There are two different ways. The first one is the loop can move or expand or rotate, creating a motional EMF. You can see because we know the magnetic flux equal what? Equal AB cosine theta, am I right? This is the area of loop. Yeah, and this is the magnetic field. This is like the angle between the axis of loop and the magnetic field. Yeah, so if you want to change the magnetic flux, which means the loop if the loop can move or expand or rotate, move, expand, which means the area will change. Rotate, which means the angle will change. Move, which means the magnetic field will change. Yeah, because maybe here has some magnetic field, but there is weaker. Like the other is stronger. That makes sense to you. This, if the loop can move or expand or rotate, it will creating a motional EMF. Yeah, actually it can change the magnetic flux based on this equation. That makes sense to you. And the second one is the magnetic field can change. Yeah, if you change the magnetic field, also you can change the magnetic flux. That makes sense to you. Yeah, the induced EMF is the rate of change of the magnetic flux through the loop, regardless of what causes the flux to change. Yeah, like yeah, the induced EMF is just the rate of change of magnetic flux through the loop. Yeah, so no matter which one, which ways you use, and the induced EMF will have. Yeah, because the magnetic flux is changed. That makes sense to you. Okay, and let's talk about how to resolve this kind of problem, like electromagnetic induction. Yeah, Faraday's law allows us to find the magnitude of induced EMFs and currents. Lenz's law allows us to determine the direction. You can see we know the induced EMF equal what? Equal delta delta t, right? And the I equal what? Equal induced EMF divide R. Yeah, like V divide R. This is Ohm's law. Yeah, so this is Ohm's this is Faraday's law. Yeah, Faraday's law allows us to find the magnitude of induced EMF and currents. And the Lenz's law allows us to determine the direction. Yeah, actually, we have already talked about a lot in next class. Yeah, we will talk about later more. Yeah, and there will be an induced EMF. Yeah, for the strategy, there will be an induced EMF in a loop occurring when the magnetic flux through the loop changes. This can occur if the magnetic field strength changes. The loop rotates. Yeah, there are some conditions. Yeah, the magnetic field strength changes, the loop rotates, which means which means the angle theta change. This one is angle theta change, and this is B change. And the loop moves in or out of the field. Actually, it's just the similar like the B change. Or the area of loop changes, which means the A area changes, because you can see the magnetic flux equal what AB cosine theta, just like we talk about that. And before resolve those kind of questions, and we need to prepare these things. Make simplifying assumptions about wires and magnetic fields. Draw a picture or a circle diagram. Yeah, use Lenz's law to determine the direction of the induced current. Yeah, and then After we prepare everything, and then we use this equation to calculate the induced EMF. Yeah, this is just a the mathematical representation is based on Faraday's law. Yeah, and for an n-term coil multiple by n. Yeah, which means if it is n-term coil, n equal what? N multiple delta T. Yeah. And the size of the induced current is this one. Yeah, because it's based on Ohm's law, it equal divide R. That makes sense to you. Yeah, and after you get the result, you just need to check that your result has a current units is reasonable and answers the question. Yeah. Okay. Let's talk about this example. Yeah, finding the induced current in a bracelet during an MRI scan. Yeah, this is a biology example. Yeah, a patient having an MRI scan has neglected to remove a copper bracelet. The bracelet is yeah, you can see the bracelet actually is a loop. That makes sense to you. 6 centimeter in diameter, which means the R should equal 3 centimeter, and has a resistance of this one. This is R, and the magnetic field in the MIR solenoid is directed along the person's body from head to foot. Her bracelet is perpendicular to B, and as a scan is taken, the magnetic field in the solenoid decreases from 1T to like 0.40 in 1.2 seconds, which means the delta equal what? Delta, like the magnetic flux change equal 4 plus 1 is negative 0.6, but you can see here you need to use the absolute value. Yeah, so it should be 0.6 T Tesla, and delta T equal 1.2 seconds. That makes sense to you. What are the magnitude and direction of the current induced in the bracelet? Yeah, here the loop area is fixed, but the magnetic field is changing. Yeah, because we know it decreases from blah, 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 which leads to a changing flux and EMF. Once we know the EMF, we can use Ohm's law to find I. So yeah, like as we follow the steps in problem solving approach 25.1. Yeah, just this one. Yeah, strategy, prepare, and solve process. And then beginning with a stretch of the situation, the figure, this figure. Yeah, shows the bracelet and the applied field looking down along the patient's body. The field is directed down through the down through the loop. As the applied field decreases, the flux into the loop decreases. Yeah, because you can see because the flux equal AB cosine theta. Here theta is 0, so it is 1. So theta is AB. Like as the applied field A decreases, the flux will decreases. Yeah, that makes sense to you. Okay. Yeah, this is and also like if the B like the B magnetic field like decreases. Also like the magnetic flux will decreases. Yeah, that makes sense to you. Yeah, here you can see the B decreases from 1T to 0.40 in 1 seconds, and the diameter is 6, so the R should be 3 centimeter, and the resistance is this one. And yeah, then you use the right hand rule, and you can see if you use the right hand rule, the induced current direction should go to this one. That does make sense to you because the magnetic flux decrease, and which means the like a loop should generate the same direction like a magnetic field, and then you use the right hand rule, and you will find the induced current direction is just like a clockwise. Yeah, that makes sense to you. Okay. Yeah, to opposite opposite the decreasing flux, and as required by Lenz's law. Yeah, to oppose like a decreasing fluxing as required by Lenz's law, the field from the induced current must be in the direction of the applied field. Thus, from the right-hand rule, the induced current in the bracelet must be clockwise. Yeah, we just talked about that. Yeah, and this is the direction of induced current, and the magnetic field is perpendicular to the plane of the loop. Yeah, we have already, yeah, this is the question gave us. Yeah, perpendicular, yeah, that is perpendicular to the magnetic field. Hence, like the theta equals 0. Yeah, because and the magnetic flux is equal this one. Yeah, because the magnetic flux should equal AB cosine theta, because theta equals 0, so this one is 1, so it is AB. And the area of the loop doesn't change with time. Yeah, and yeah, because this doesn't change with time, but B does. Yeah, because we know like the magnetic field decrease. Yeah, so the like flux what we here means delta. Yeah, so the magnetic flux change equal this one equal, yeah, equal this one, because this is magnetic field change, and the change in the magnetic field during like delta t equal 1.2 seconds is this one. Yeah, actually we have already calculated just now. According to Faraday's law, the magnetic the magnitude of the induced EMF is equal to this one. And then we just here this is like A delta B. Yeah, and delta B equals this one, and then we can calculate. We put a pi, put a R here, and put a delta B here. The delta like the time difference here, and then we can like calculate the induced EMF is equal to this one, and the current induced by this EMF is equal. Yeah, we use the Ohm's law, and then we can get the induced current is 0.40 like yeah, the decreased magnetic field causes uh 0.40 clockwise current during the 1.2 seconds. That the field is decreasing. Yeah, this is the result we calculate. And then let's assess this result. The EMF is quite small, but because the resistance of the metal bracelet is also very small, you can see, although the EMF is small, but the resistance is also small, so the current is respectable. Yeah, electromagnetic induction produces currents large enough for practical applications, so this result seems plausible. Yeah, the induced current could easily distort the readings of the MRI machine, and a larger current could cause enough heating to be potentially dangerous. So operators are careful to have patients remove all metal before an MRI scan. Yeah, so that's the reason why, if one patient go to have the MRI scan, he needs to remove every metal things from his body or her body. Yeah, otherwise it should be very dangerous, because it will maybe the resistance, because usually because this, if there is a metal, the resistance will be small. Yeah, smaller, and then you can see, and the current will be bigger. Yeah, maybe it will, yeah, it will like harm your body. Yeah, so just be patient, pay attention, just pay attention to that, and be careful when you or your family do the MRI scan. Yeah, okay. Let's talk about this example and problem. In the following figure shows a 10 centimeter diameter loop in three different magnetic fields. The loop's resistance is 0.1 ohms. For each situation, determine the magnitude and the direction of the induced current. Yeah, actually, I think this one, yeah, you just use the Faraday's law to calculate uh, the induced EMF delta by delta T, and then use Ohm's law to calculate the current. Yeah, so you can see for the first one, and yeah, the increasing at yeah, this is for you determines this is increasing at 0.5 t seconds, which means the EMF should uh, should equal, yeah, the A area is like 10 centimeter diameter, which means pi r, and then you need to use 5 centimeter as r and calculate the area, and then you can calculate, you can go to the this is a delta B, because this is 90 degrees. Am I right? Sorry, it's 0 degree. The cosine theta is 1, so it is AB and then delta T. Yeah, this one is just equal this one. Am I right? And then you multiple for, and then you can go this one, and then you can like get the I equal yeah, this is this one. This is like uh, B, this is yeah, equal B, yeah, mm, this is A, yeah, here, yeah, that makes sense to you. Yeah, let me make it more clearly. Yeah, yeah, R equal 5 centimeter, and we know like A, this one A equal pi R square, and like the induced EMF equal this one and equal what? A, because A does not change, so it is delta B delta T. Yeah, you can put it into, yeah, it's just the delta, this phi, and then equal pi R square and multiple, this is just like this one. Yeah, 5.ts, and then you can go the like EMF, and then you can use the ohm like law to calculate the current, because you know the resistance. Yeah, and for now it is increasing. Yeah, so the the magnetic field is increasing, which means the loop should generate a opposite like a direction. So then you can use the Ohm's law to decide the induced direction. It's just like this. Yeah, for this one, yeah, it's just the similar thing, but it's just a decreasing. But although this is decreasing, yeah, decreasing, which means you need like the loop should generate the like same direction magnetic field. So it should like this. The direction should, generated a magnetic field should like this. So the current direction is just still like this. Yeah, the direction doesn't change. Yeah, and then the EMF, yeah, induced EMF is also equal A delta B delta T, and yeah, the A doesn't change, and the delta B is just the decreasing. It should be negative, but this is like a absolute value, so it's just a pi R square multiple 0.5, and then you use the Ohm's law to get the current. Actually, although this one is increasing, this is decreasing, but the current is just the same thing. And this one, you can see it's decreasing at 5 point t. But you can see here, the AB, the magnetic fluxing is equal AB cosine theta. For this situation, the theta equal what? The theta equal like 90 degree, which means this is 0. So the magnetic flux is always 0. So which means there is no current for this situation. Does it make sense to you? Yeah, think about that. Yeah, so which means this current is 0. Okay. Yeah, you can resolve those problems by yourself and just use Faraday's law, Ohm's law, and the right-hand rule, Lenz's law to find the direction of current. Okay. Okay, let's talk about this one situation, one phenomenon. We call it eddy currents. Let's talk about what is eddy current. Yeah, you can see currents. And take a sheet of copper and place it between the pole tips of a strong magnet. You can see there is a strong magnet, and then you take a sheet of copper and place it between those two. And now pull the copper sheet out of the magnet as fast as you can. Surprisingly, it takes a significant effort to pull the metal through the magnetic field. Yeah, there will be this situation. Like if you put a copper sheet here, and if you pull the copper sheet as far as you can, you will find it's very difficult to pull it out. Yeah, let's analyze this situation to discover the origin of the force. Okay. There are two loops lying entirely in a metal sheet between two magnets. You can see here. Actually, yeah, there are two loops lying entirely in a metal sheet between two magnets. Yeah, here, this is the downward fluxing through this loop. There is a two loop, and as the sheet is pulled, the loop on the right is leaving the magnetic field, and the flux is decreasing. You can see if you put out the sheet, and the loop on the right, on the right is leaving the magnetic field, and the flux is decreasing. Does it make sense to you? Yeah, according to Faraday's law, the flux change includes a current to flow around the loop. Yeah, Lenz's law says the current flows clockwise. You can see if it's leaving, it will generate the same direction goes into. Yeah, so if you use the right hand law, and you will find the current direction is just clockwise. Yeah, doesn't make sense to you. And then the loop on the left side of the metal enters the field, and so the flux through it is increasing. Yeah, because you can see at the beginning it's just like it's just some part it is in this sorry in this field, but some part is not. So when it goes to this direction, and the flux through it is increasing, which means it will generate opposite direction. And then if you use Lenz's law, and you will find the current is counterclockwise. Yeah, the Lenz's law requires the induced whirlpool current on the left loop is counterclockwise. Okay. And eddy currents as a spread out whirlpools of an induced current in a solid conductor. Both whirlpools of current are moving in the same direction as they pass through the magnet. Yeah, the magnetic field exerts a force on the current opposite the direction of pull, acting as a braking force. Yeah, you can see like You can see this two. Yeah, you can see it has sorry. Yeah, we call this current eddy currents. Actually, they are spread out wheel poles just like this of an induced current in a solid conductor. Yeah, because those currents are moving in same direction. Yeah, you can see in same direction as they pass through the magnet. Yeah, the magnetic field exert a force on the current and opposite the direction of pull, acting like a braking force. That makes sense to you. Okay, because of the braking force exerted by the magnetic field, an external force is required to pull a metal through a magnetic field. If the pulling force ceases, the magnetic braking force quickly causes the metal to decelerate until it stops. Yeah, magnetic braking uses this braking force to slow trains and transit system vehicles. Yeah, we just use this kind of like eddy currents. Yeah, like to use it like to slow trains and transit system vehicles. Yeah, it is amazing. Yeah. Okay. You can also view the video to see more about magnetic braking. Yeah, but this is kind of this is an application for like a induced current. Yeah, if we how we use this like how this situation happen and how can we use this situation to use it in the real world. That makes sense to you? Okay. Let's continue talk about that one for another like application for eddy currents. Yeah, in a technique called transcranial magnetic stimulation, we call it TMS. A large oscillating magnetic field is applied to head via a current carrying cord. Yeah, you can see there is a large current is quickly switched on. Yeah, the field produces small eddy currents on the brain. Yeah, this one. And inhibiting the neurons in the simulated region. This technique can be used to determine the importance of stimulated region in certain perceptions or tasks. Yeah, you can see we just use there is a loop and we use this loop to like generate a small like adding currents in the brain on the brain and this resulting rapid change in flux induces eddy current in the brain tissues. And this technology can be used to determine the importance of the stimulated region in certain perceptions or tasks. Yeah, this one can help the scientists to find when we do some task, when we maybe do sports, when we do some things, which area is activity, and then it will help like the scientists to improve our brain or find some like cure method for some like a specific disease. Does that make sense to you? Okay, let's continue. Yeah, let's check this example problem. A coil used to produce changing magnetic field in an TMS device produces a magnetic field that increases from 10 Tesla to 2.5 Tesla in a time of 200 ms. Suppose this field extends throughout the entire height. Estimate the size of brain and calculate the induced EMF in a loop around the outside of the brain. Yeah. Firstly, yeah, here, actually this one is not difficult. Yeah, because this one is just let us to calculate the induced EMF, and we use this equation delta phi divided delta t, and here we know it is a. Yeah, a usually is not changed. It's just yeah, this is just this similar like this one. Yeah, the A is just the area of your brain like that, and the here here is just a delta B, the magnetic field change, and delta T. Yeah, we have already know the delta B. Yeah, it is 2.5 T because 2.5 T minus 0, it is 2.5. And this is the tab. Yeah, and then what we need is just estimate the size of the brain. Actually, when you estimate the size of brain, what you just need to do is uh, just use your brain. Yeah, yeah. Like or you can check it online. Like usually, the radius of our hand is about 8 centimeter. Yeah. So you just use this number to calculate the area, and so the area of loop equal pi r square is pi 0.0. Yeah, you need to change the unit, and then you can use this equation to calculate the induced EMF. It is around like 250 volt. Yeah, that makes sense to you. Yeah, so just here, just estimate the size of our brain. It's just usually, yeah, our brain, the radius of our brain is 8 centimeter. Yeah, you can check it online. Yeah, this is just a common sense. Okay. Okay, let's talk about electromagnetic waves. Yeah, we have already talked about more about electromagnetic induction. Yeah, here we talk about using Faraday's law to calculate the induced EMF, and then use Ohm's law to calculate the current, and then we use the Lenz's law to decide the direction of current. Okay, then we talk about the electromagnetic waves, and you can also view this video to see what is electromagnetic waves. Yeah, get some initial ideas. Yeah, but I will not play this video here. Okay, and suppose we have a solenoid of radius R1. Yeah, this one. Yeah, this is a R1 solenoid. Uh, like that passes through the center of a conducting loop. Yeah, there is a loop, and this loop have a larger radius R2. The solenoid carries a current and generates a magnetic field, but the magnetic field outside the loop is zero. Yeah, which means only inside has a magnetic field. Yeah, what happens to the loop if the solenoid current changes? Yeah, our theory predicts an induced current in the loop. Like how can the change occurs in the conducting loop possibly know that the magnetic field inside the solenoid is changing? Yeah, there are some questions we need to think about that. Let's talk about like those questions. Yeah, to answer the questions, we will first consider a related question. When a changing flux through a loop induces a current, what actually causes the current? What force pushes the charges around the loop? Yeah, actually, yeah, you can see if you want to if you want to generate a current, you want to cause a current, there will be the motion of the charge. We know when we talk about the current, we know the current is the motion of charge. Am I right? So what causes this motion of the motion of charges, and what makes these charges like move, and like what force pushes the charge around the loop? Yeah, we know that an electric field can move charges through a conductor. Yeah, this is we talk about in chapter 22. Yeah, you can review it. And a changing magnetic field creates an induced electric field. Yeah, you can see actually a changing magnetic field not only creates induced EMF, induced current, it also creates an induced electric field. Actually, this is just from the basic reason like why there is a like induced current, because there is an induced electric field, and then there is a induced current. Does it make sense to you? Okay. An increase in magnetic field directed into the screen induces a current in a loop in the counterclockwise direction. And this is what we talk about in many times. The induced electric field must be tangent to the loop at all points to make the charges in the loop move. And you can see the induced electric field. Yeah, this this one is induced like electric field must tangent to the loop at all like points, like to make the charges in the loop move, because here the charge every point it should move to this way. It just along the direction of electric field. Yeah, doesn't make sense to you. Okay. And an induced electric field is produced by a changing magnetic field, whether there is a conducting loop or not. Yeah, actually, you can see here, this is an induced electric field, like E. Yeah, an induced electric field is produced by a changing magnetic field, whether there is a conducting loop or not. Yeah, if like there is a changing magnetic field, there must be a like induced electric field. Even there is no loop here, there is no like a conducting loop here. Yeah, that makes sense to you. Yeah, what about a changing electric field? Yeah, if we change electric field, is there a like a induced magnetic field? Yeah, do you think, what do you think? Yeah, just as a changing magnetic field produces an induced electric field, a changing electric field creates an induced magnetic field. Yeah, it's interesting, am I right? It's amazing, am I right? Yeah, like the uh changing those two, just like one can create it, the other, the other also can create it, like the original one, like the changing electric field can create an induced magnetic field. A changing like a magnetic field also can like create like a an induced electric field. Yeah, just remember that. Yeah, a changing magnetic field can induce an like uh, an electric field in the absence of any charges, and a changing electric field can induce a magnetic field in the absence of any current. Therefore, it is possible to sustain a magnetic or electric field independent of charges or currents. Yeah, a changing magnetic field can induce a magnetic field which can charge in just the right way to recreate the electric field, which can change to recreate the magnetic field. The fields are continuously recreated through electromagnetic induction. Yeah, electric and magnetic fields can sustain themselves free of charges and currents in the form of an electromagnetic wave. Yeah, this is what we just got the solution, like a summary we get from what we observe. Yeah, those it's yeah. And why it has this like feature characters? Yeah, because actually electric fields and magnetic fields, it it can sustain themselves free of charge and current, and in the form of electromagnetic wave. Yeah, it's just like can act like the form of an electromagnetic wave. Yeah. Okay, let's continue to talk about yeah, and then let's talk about properties of electromagnetic waves. Yeah, yeah. An electromagnetic wave. Firstly, it is like a transverse wave. It's not a longitudinal wave. Yeah, and an electromagnetic wave travels with the speed. This one. Yeah, we can use this equation to calculate the speed of electromagnetic wave. Yeah, and this one, yeah, this one, and this is the same thing. Sorry, I think I just should make it constant. Yeah, this one and this one, those two are the permittivity and permeability constants. Yeah, those two are constants. Yeah, and if you insert the known value, we find that yeah, this like velocity speed just equal 3 multiple turn 10 power 8 meter per second. It's just the speed of light. See, that's the reason when we calculate, when we resolve some problem, we talk about the speed of electromagnetic wave. We use this value, yeah, because after calculating, it's just the spin of the light C. Yeah, that makes sense to you. Okay. And James Clerk Maxwell, yeah, the first to complete this analysis concluded that yeah, light is an electromagnetic wave. Yeah, this is when we talk about the light, we know like light is has two different like form. Yeah, one is like wave, the other is a ray. Am I right? And also, like the light is also it is an electromagnetic wave. Yeah, because we also talk about it is has the third one like a photon like a particle. Yeah, it's just the third form. Yeah, and we just I told you like we will talk about in chapter like 25. Yeah, this is the third form, like it is also an electromagnetic wave. Yeah, you can see this is how the Maxwell found that. Yeah, the wave, the light wave is a sinusoidal travel wave with frequency f and a wavelength lambda. And here E and B are perpendicular to each other and to the direction of travel. Thus, an electromagnetic wave is a transverse wave. Yeah, this is just tell us why the electromagnetic wave is a transverse wave, because like the here E and like B are perpendicular to each other and to the direction of the travel. Yeah, and E and B are in phase. That is, they have matching crests, downs, and zeros. Yeah, this is just like the like a net wave. Okay. Yeah, at every point on, yeah, this is like an electromagnetic wave. Yeah, and at every point on an electromagnetic wave, the electric and magnetic field strengths are related by, yeah, they just they have this form, they have this relationship. E divided B equals C. C is just like the speed of letter C. Yeah, that makes sense to you. Okay. And we learned that we can relate the speed, frequency, and wavelength of a sinusoidal wave as using this equation. Yeah, this we talk about when we in chapter I think 70. Yeah, like that. And for electromagnetic waves, the relationship between this one, because the V equals C, am I right? So then it should equal this one. And yeah, so this is just the feature. Yeah, this is just the how the like what the like electromagnetic waves looks like, and it's just like has this has E and for magnetic electromagnetic waves, it has it involve two different like features, like a magnetic field and electric field, and those two like just interact with each other and like travels like a transverse wave. Yeah, in the At every point, yeah, you can use this equation to find the relationship between the electric field, magnetic field, and the speed of the electromagnetic waves. And does it make sense to you? Yeah, you also can use this equation to yeah, because this C, yeah, we usually know that, and you can use this equation to calculate the wavelength or the frequency for the electromagnetic waves. That makes sense to you. Okay, yeah. The displacement of a plane wave is the same at all points in any plane perpendicular to the direction of motion. If an electromagnetic wave were moving directly toward you, the electric and magnetic waves would vary in time, but remain like a central, but remain synchronized with all other points in the plane. Yeah, as a plane wave passes you, you would see a uniform oscillation from the electric and magnetic fields of the wave. You can see here. This is as the time pass. What the like the magnetic fields and the electric field waves looks like. Yeah, this one. Uh, this this is the magnitudes of the fields are E0 and B0 at this instant. Yeah, and this blue one is the magnetic field, and this red one is the electric field. Yeah, the electric and magnetic field are the same at all points in this plane. Yeah, as time passes, the electric and magnetic fields change at all points in the plane. Yeah, you can see as the time pass, it all change. Yeah, the electric and magnetic fields are zero twice each period. Yeah, you can see if the like each like twice each period, and the electric field and the magnetic field are zero, and then as the time passing, it will change. Yeah, that makes sense to you. Okay. And this is just the like details for how the magnetic fields and the electric fields change. Yeah, this is t equals 0 when t equals 0, and the magnetic for every point. Yeah, the magnetic field and the electric field are same. Yeah, and you can see this is a magnetic fields. Yeah, and this yeah, the electric and magnetic field are the same at all points in this plane. And as time passing, this is t equal the period divided by 8. As time passes, the electric and magnetic fields change at all points in the plane. Yeah, at the same time. Yeah, and like twice each period, you can see twice each period, the electric and magnetic fields are 0. It will become 0, and then it will like in, increase to get at the same time. You can see at the beginning it's just like this, and then it decreases at the same time, and until to 0, and then it will increase, yeah, but different direction. And as the time passing, yeah, it will get to the highest, yeah, the maybe the biggest, yeah, and then like as the time passing, it will like repeat again and again. Yeah, that makes sense to you. It's just a period wave. Yeah, if a plane electromagnetic wave moves in the x direction with the electric field along the y direction, yeah, then the magnetic field is along the z axis. Yeah, and the equation for the electric and magnetic fields of a wave with a period t and wavelength lambda are this one. Yeah, this is just the like electric field equal this one, and the like the magnetic field equal this one. Yeah, E0 and B0 are the amplitudes of the oscillating fields. Yeah, you would, and the amplitudes of the fields in an electromagnetic wave must be related. Yeah, they have this relationship. Yeah, relationship between the field amplitudes for an electromagnetic wave. Yeah, since the value of C is so large because it's equal like 3 multiple 10 8. Yeah, the electric field amplitude in NC is much larger than the, yeah, because you can see this result is large, very large. So which means this one compared with this one is much larger than the like a magnetic field amplitude in T. That makes sense to you? Yeah. Okay. Yeah, this is for some. Yeah, all the properties of electromagnetic waves. Yeah, we talk about that, and yeah, we talk about like the electromagnetic yeah, and this is for the electromagnetic waves. It is a transverse wave, and the speed is just the same as the speed of light, c. And then we talk about the also light is an electromagnetic wave. Yeah, light is not only a rain. It not only is a rain. It's not only a wave. It's also electromagnetic wave. Okay. Also, and the for the electromagnetic waves, the electric and the magnetic field strengths have this relationship. Yeah, and also the for the electromagnetic wave, and it has the wavelength and the frequency uh, have this equation. And after that, we talk about like how the for the magnetic waves, how the electric field and the magnetic field change as the time pass. Yeah, and then we talk about like the if a plane like a electromagnetic wave moves in s direction in the electric field along the y-axis, and the magnetic field is along the z axis, and how to calculate the like magnetic waves and the electric field and the magnetic field. Yeah, and then the E0, B0 is the amplitude of the oscillating fields. And after that, we talk about the, yeah, and also we talk about the relationship between the amplitude of like of the fields in electromagnetic waves. Yeah, must related. Yeah, you in this relationship. Yeah. Like we also talk about like if because this one is large, very large, so this one is must larger, much larger than this one. Yeah. So this is the properties of electromagnetic waves. Okay, let's talk about the other term like polarization. Yeah. You know the plane containing the electric field vectors of an electromagnetic wave is called the plane of polarization. The figure shows a wave traveling along the axis. Yeah, this direction. And so the plane of the polarization is the XY plane. Yeah, this wave is vertically polarized. The electric field is oscillating along the y like axis. Yeah, you can see here. The wave is moving toward to you. Yeah, you can see this one means it toward to us out of the plane. Yeah, and this is a vertical polarization, and this one is a horizontal like a polarization. Yeah, because we know like we only like check the electric field move. Yeah, because you can see here like the plane containing the electric field vector of electromagnetic wave is called the plane of polarization. Polarization. Yeah, only like contain the electric field vector, not the magnetic field vector. Yeah, so which means in this picture, yeah, this plan, we call it a plan of polarization, because yeah, and this is vertically polarized. And then since based on that one, we know this one is just this is like a electric field, so which is a vertical polarization. And for this one, because this is a electric field, so we call this horizontal like a polarization. And for this one, this is 30 degrees, so we call it like a polarization 30 degrees from vertical. Vertical. Does it make sense to you? Okay, each atom in the sun emits light independently of all other atoms, so the polarization of each atom is in a random direction. The superposition of the waves from all of the different atoms results in an unpolarized wave. The radiation from most sources of electromagnetic radiation is unpolarized. This is some features for polarization. Like each atom in the sun emits light like independently from all other atoms. So the polarization of each atoms is in a random direction. The superposition of waves from all of the different atoms result in an unpolarization wave because of superposition features. The radiation from most sources of electromagnetic radiation is unpolarized. This is some like facts. We need to understand. We need to know. And then here is a video for like a parallel wire polarizer for microwaves. You can. It's an application for polarization. You can check it. I will now play it here. Okay. Let's talk about the energy of electromagnetic waves. The energy of electromagnetic wave depends on the amplitudes of the electric and magnetic fields. In chapter 50, actually this one you should learn like in physics 1, college physics 1. We define intensity to be this is intensity equal P divided A. Here, P is the power or energy transferred per second, or a wave that impinges on the area A. So this is the power, this is the area, and then this is the intensity. And then we have this equation. I equal P divided A equal half C, and this one multiple this one, multiple this thing. This is this what is this? We just talked about this. Do you remember that? This one. E0 and B0 are the amplitudes of oscillating fields, which means it's a maximum like maximum electric field and a maximum magnetic field. So here, like the intensity equal to half C multiple this constant and multiple amplitude, the maximum electric field square, and also equal half C divide this constant multiple magnetic field, maximum magnetic field square. So this is the intensity of an electromagnetic wave with field amplitudes E0 and B0. The intensity of a plane wave, like a laser beam, does not change with distance. The intensity of a spherical wave, which spreads out from a point, must decrease with the square of the distance in order to conserve energy. If a power source emits uniformly in all directions, the wave intensity at a distance r is, we use this equation. This is for like a power source that emits uniform in all directions. This is power, and this is like the area. And this is just in all directions, and this is intensity. Okay, and okay, let's check some questions for this like energy of electromagnetic waves. And to double the intensity of an electromagnetic wave, you should increase the amplitude of the electric field by a vector of what one? Yes. Firstly, let's write the equation here. Yeah, we know this equation, which means the I equal what? Let me write it down, and then you will know it clearly. Yeah, here let's write the equation I equal half C, and this is just the constant E0 square. Yeah, so which means if we want to double the intensity, yeah, so how should we increase the amplitude? This one, which means it should like we need to let it equal to I, which means if other, yeah, because other cannot be changed, this is fixed and this is fixed. So what we just what can change is just this one. So if this one equal square root 2E0, and then it will equal what? 2C. That makes sense to you. So which means it should by a factor of this square root 2. Yeah, so it should be this one. That makes sense to you. So it should C. Yeah, because the intensity like a proportional like E0 square. Okay, let's check the other one. Yeah, and here like this is like a summarize for electromagnetic waves. Yeah, an electromagnetic wave is a transverse wave of oscillating electric and magnetic fields. Yeah, actually the electromagnetic waves is just combination like the electric and magnetic fields combination like that. Yeah, the magnetic wave, electromagnetic wave is a transverse wave. Yeah, and then here are some like features. Yeah, you can find this image in page 896. You can see here. The electric field and the magnetic field are perpendicular to each other. Yeah, we know that. Yes, electric field amplitude is E0, which means the maximum electric field. And the B0 is just the maximum magnetic field. We call it a magnetic field amplitude. And the ratio of the amplitude of the electric and magnetic fields is the spin of net. Yeah, they have this relationship. And also the polarization is defined by the orientation of the electric field. Yeah, so it's just an electric field. It's none of business with the magnetic field. Okay, the direction of travel is perpendicular to both E and B. You can see this is a travel direction. So it's just perpendicular to this one and also this one. Yeah. So, which means this is a transverse like a wave. And EM wave travel at the speed of light. So the fundamental wave relationship is this one. Yeah, we talk about that. And this is just the line of speed in vacuum. Okay. And an electromagnetic wave is a transverse wave of oscillating electric and magnetic fields. The intensity of the EM wave depends on the field amplitudes. Yeah, we have this equation. Yeah, it equal this one, also equal this one, and these two are two constants. This one is a permittivity constant. Is around this is this value, and this one is a permeability constant. Yeah, is this one. And then the intensity of an EM point source decreases with the distance from the source. You can see because it equals this one. So which means it decreases. Like if the distance like increase and it will decrease. Does make sense to you? Okay. And let's talk about this example problem. Yeah, and this example problem, let me read it. Inside the cavity of a microwave wave oven, the 2.4 GHz electromagnetic waves has an intensity. This one. What is the strength of the electric field and the magnetic field? Yeah, since let's just write the equation here, and you will know that. Yeah, we know I equal what? I got half C 0 E equal half C mu 0 B 0 square. And then now we know the I am right intensity. And then here we know the C, we know the this constant, and then we can calculate the amplitude of the electric field. Am I right? And also for this one, yeah, because we know this C and we know this constant, we also can calculate the amplitude for the magnetic field. Does it make sense to you? Yeah. Okay. Yeah. This one I think it is not difficult for you. Yeah, actually, you can see if you observe this equation, actually the intensity is it had been it's non-business with like the frequency. Yeah, the frequency doesn't affect the intensity or electric field or magnetic field. Yeah, just pay attention to that. Okay. Let's talk about this example. Yeah, electric and magnetic fields of a cell phone. Yeah, a digital cell phone emits point 0.6 volt of 1.9 GHz radio waves. What are the amplitudes of the electric and magnetic fields at a distance of 10 centimeter? Yeah, we will solve this problem using details from synthesis 25.1. It's just this one. Yeah. Yeah, you can see here, you have this equation, you have this equation, and you also have this equation, and then you using those equations, you can resolve this problem. Yeah, we can approximate the cell phone as a point source. So we can use the second intensity equation to find the intensity at 10 centimeter. Once we know the intensity, we can use the first intensity equation to compute the field amplitudes. Yeah, like firstly, we use the second equation. Yeah, we know the power. Yeah, the question is also give us. And then we know the distance. Yeah, the here is the distance. And then we can calculate the intensity. Yeah, after we know the intensity, we can use this equation. We can use I equal half C B0 square, and then we use this equation to calculate the amplitude of electric field. And we also can use this equation I equal half C mu 0 B0 square to calculate the the magnetic field amplitude of magnetic field. Also, you can use this equation like B E0 divided B0 equals C. This equation to calculate the amplitude of magnetic field. Also, does it make sense to you? Okay, yeah, you can see the electric field amplitude is reasonable small. Yeah, it is this one. And for comparison, the typical electric field due to atmosphere electricity is 100 volt per meter. The field near a charged Van de Graaff generator can be 1,000 times larger than this. The scale of the result thus seems reasonable. We know that the electric fields near a cell phone is are not large enough to produce significant effects. Yeah, the magnetic field is smaller yet, only one only this of the Earth's field, which, as you know, is quite weak. This makes sense as well. You haven't noticed the magnetic effects while making the phone call. That makes sense to you? Okay, let's continue to talk about more. Yeah, let's talk about polarizers and changing polarization. Yeah, we can transfer unpolarized light into polarized light with a polarizing filter. Yeah, a typical polarizing filter is a plastic sheet containing long organic molecules called polymers. Yeah, and this is just an application for the polarization thing. Yeah, and you can see this one is polymers, and you can see this part is unpolarized light consistent with the polarized in all possible direction. And after this filter, and only the components of electric field parallel to the axis is transmitted. Yeah, and all this is how the polarizing filter work. Yeah, and as light enters a polarizing filter, the component of the electric field oscillating parallel to the polymers, yeah, drives electrons up and down. Yeah, to the polymers. Yeah, the component of electric field oscillating parallel to the polymers drives electrons up and down the molecules, which absorb the energy from the light. Yeah, which means the polarizer, yeah, these polymers will observe the other direction's light and only pass this direction. Yeah, and only the component of the light polarized perpendicular to the polymers emerges. Yeah, the direction of the transmitted polarization is the axis of the polarizer. Yeah, that makes sense to you. Okay. And when polarized light approaches a polarizer, the amplitude of the electric field of light transmitted is, yeah, this one. Yeah, this is the this is like a electric field of incident light, and this is a transmitted light, like electric field of transmitted light, and then they have this relationship. Yeah, you can see the incident light is polarized at angle theta with respect to the polarizer's axis. Yeah, this is a polarizer axis. Yeah, and only the component of electric field in the direction of the axis is transmitted. Yeah, only this direction is transmitted, and this one will be observed. Absorbed. Yeah. Okay, let's continue. Like the intensity depends on the square of the electric field amplitude. So the transmitted intensity of light from a filter is related to the intensity of the light, the incident light by Mallows law. Yeah, this is another Mallows law. Yeah, we use this equation. Intensity transmitted light equal as intensity incident light multiple cosine theta square. Yeah, this we call it Mallows law. Yeah, Mallows law for transmission of polarized light by a polarizing filter. Yeah, you can see Mallows law can be demonstrated with two polarizer filters. The first is called the polarizer, yeah, which creates the polarized light, and the second filter is called the analyzer, yeah. Yeah, this one is, we call it a polarizer, and this is analyzer. The analyzer is rotated by an angle theta relative to the polarizer. Yeah, which means you can see if you this is the angle. Yeah, the analyzer is rotated by an angle theta related to the polarizer. Yeah, so which just explain what's this theta. Yeah, okay. Like when a polarizer and an analyzer are aligned, yeah, which means the theta equals 0, the transmission of the analyzer should be 100%. Yeah, the intensity, you can see if like this one, if the theta equals 0, which means this one is 1, like the transmitted intensity equal incident intensity, and also for the electric field, yeah. And the intensity of the transmission mission decreases to 0 when theta equal 90 degree. Two polarizing filters with perpendicular axis are called crossed polarizers, and they block all the light. You can see this is for the theta equals 0, which means the transmission of the analyte should be 100%. This is half. Yeah, the red lines show the axis of the polarizers, and this is 90 degree, which means you can see this one. It's black, all black, which means they block all the light. Yeah, that makes sense to you. Yeah, you can check this video for changing the angle and change the transmission for a polarizing filter. Yeah. And then we talk about the other applications. Yeah, an object placed between two cross polarizers can change the polarization of light so that light is transmitted from the analyzer. Yeah, like different materials and different material in teeth change the polarization of light in different ways. They can give an image of a different tassel in teeth. You can see here. Yeah, and if you use different materials, yeah, in teeth, and then you will you can get an image of different texture in teeth. Yeah. Okay. Yeah, in polarizing sunglasses, the polarization axis is vertical, so the glasses transmit only vertical light, which means why when you wear the sunglasses and you will not affected by the bright sunshine. Yeah, glare is a reflection of sunlight from lakes and other horizontal surfaces. It has a stronger horizontal polarization, so vertically polarized glasses eliminate that glare. Yeah, that makes sense to you. Okay, let's check some questions. Yeah, vertically polarized light wavelength intensity 1000 and it's coming toward you. Out of the screen after passing through the polarizing filter, the waves intensity is which one? Yeah, since the intensity the transmission equal I incident cosine theta square. Yeah, which means this one is 1000 and the cosine 45 equal what? Yeah, this one equal 5 0.5, so it is 500 Wm. Yeah, just use this equation. Yeah, it is B. Yeah, just use this equation. Okay, let's continue. Yeah, let's talk about this example problem. Yeah, light pass through a polarization filter has an intensity of 2 watt per square meter. How should a second polarization filter be arranged to decrease the intensity to 1.0? Yeah, we know like the I transmission equal I incident multiple cosine theta square, and here like this one is 2, and this one, if we want to this intensity like decrease to 1, which means this one should be equal 5.0, and then we just got it the cosine 45 degree equal 0.5. So which means we just arrange like this second filter like the theta should equal like 45 degree. That makes sense to you? Yeah, we just use this is Maslow's law to find the intensity of light through the second filter. And then got the theta. Theta is 45, and then you put the second polarization filter with a 35 angle. Yeah, that makes sense to you. Okay, let's talk about the next part, like the photon model of electromagnetic waves. Okay, we have learned that light is a wave, but many experiments convincingly lead to the surprising result that electromagnetic waves have a particle-like nature. Yeah, photons are the particle-like component of electromagnetic wave. Yeah, you can see this. There is one experiment. Yeah, one experiment that indicates the particle-like behavior of waves is a dim photograph. If light acted like a wave, reducing its intensity should cause the image to grow dimmer, but the entire image would remain present. Yeah, you can see this is like at low level, light level, we see individual points as if from particle, and this is at higher light levels. We don't see the particle-like behavior. Yeah, if you increasing, yeah, if you decreasing light intensity, and you will find the light has a particle-like behavior. Does it make sense to you? Okay, in actually, a dim photo shows that only a few points on the detector registered is the presence of light, as if the light came in pieces. When the intensity of the light increases, yeah, you can see increases, the density of the dots of light is high enough to form a full picture. Yeah. And the photon model of electromagnetic waves consists of 3 basic postulates. Yeah. Like the first one is electromagnetic waves consist of discrete massless units called photons. Yeah, a photon travels in a vacuum at the speed of light. Yeah, and the photon model of electromagnetic waves consists of 3 basic postulates. This is the second one. And each photons have energy. Using this equation, you can calculate the energy from each photon, where here F is the frequency of the wave, and H is the universal constant. We call it Planck's constant. The value is equal to this one. In other words, the electromagnetic wave comes in discrete chunks of energy HF. Yeah, the higher the frequency, the more energetic the chunks. Yeah, that makes sense to you because we just got this equation. And the third postulate is the superposition of a sufficiently large number of photons has characteristics of continuously electromagnetic wave. Yeah, this is three basic postulates for the photon model of electromagnetic waves. Yeah. Yeah, okay. Yeah, and let's review some questions. A typical analog cell phone has a frequency of 850 amhertz, and a digital like phone has a frequency of 1550 megahertz. And compared to the signal from an analog cell phone, the digital signal has, yeah, it let us to compare the energy and the wavelengths. We know the like energy E equal HF. H is a constant, which means which one has a higher frequency and which one has a higher energy. You can see the digital like phone has a higher energy frequency, which means it has a higher like photon energy. Yeah, so those two, yeah, we choose from those two, and then we know like the C equal lambda F. I'm right because it let us to compare the wavelengths. So which means the wavelength equals C divided F, which means which one has mm, like a if it has a bigger like a frequency, it has a smaller wavelength. Am I right? Yeah, from this equation. So which means the digital signal has a shorter wavelength and higher photon energy. Yeah, the answer should be D. Does it make sense to you? Okay, let's check this one. A radio tower emits 250-volt signals. One an AM signal at a frequency of uh 550 kHz, one an FM signal at a frequency 55 megahertz. Yeah, which signal has more photons per second? Yeah, we know like the E equal HF, right? This is constant. So like the F signal has a like a the higher frequency, which means this FM signal has a higher energy. Am I right? But you can see those two energy has the same power. Yeah. So which means if this like AM AM signal has a lower like energy, but if they have the same power, which means AM signal should have more photons per second to generate the same like power. Does it make sense to you? So which means the AM signal has more photons per second. Yeah, does it make sense to you? Okay, let's talk about this example. Like finding the energy of a photon of visible light. Yeah, 550 nanometer is the approximate average wavelength of visible light. What is the energy of a photon with a wavelength of 550 nanometer? Yeah, a 40-volt incandescent light bulb emits about 1 G of visible light energy every second. Estimate the number of visible light photons emitted per second. Yeah, actually, those questions are not very difficult for you if you know the relationship between the wavelength, frequency, energy, the power, and you will know how to resolve this problem. Okay, let's check this example. In the yeah, the energy and the frequency of for the sorry. Let me drink some water. Yeah, by equation 25.22. Yeah, it's just this equation, E equal HF. Yeah. And once we know the photon energy, we can find the number of photons it would take to have the total energy of this one. In the yeah, the frequency of photons, we can use this equation. C equal lambda f to calculate it. Then we can get the frequency for the photon. And also like equation 25.22 gives us the energy of this photon, like this equation. And now we know the h is just a constant value, and this is frequency. And then we can get the energy for the photon. Yeah, this is an extremely small energy. Yeah, in fact, photon like energies are so small that they are usually measured in electron volts, yeah, EV, rather than joules. Yeah, recall that 1 EV equal this one. Yeah, with this, like we find that the photon energy is this one. Yeah, like this one. Yeah, we can use EV to represent the energy. Yeah, just use different like units, but it's the same thing. Okay, and then like this is is the energy of photon. And then we find the photons emitted by a light bulb span a range of energies because the light spans a range of wavelengths. But the average photon energy corresponds to a wavelength near 550 nanometer. Thus, we can estimate the number of photons in 1 G of light as yeah, this number, yeah, because the like one photon is you has this like energy, so 1 G and it needs these photons. Yeah, a typical light bulb emits about 3 multiple 10 power 80 photons every second. Yeah, it's a lot, am I right? Yeah, okay. Let's assess this result. Sorry. Yeah, the number of photons emitted per second is staggeringly large. It's not surprising that in our everyday life we sense only the river and not the individual particles within the flow. Yeah, that makes sense to you. Yeah. Okay. Let's continue to talk about the photon model of electromagnetic waves. You can see a single photon of light with a wavelength of 550 nanometer has energy of this one. Yeah, we just calculate it. Yeah, depending on its energy, a single photon can cause a molecular transmission as it does on the sensory system of an eye, or even break covalent bonds. Yeah, the photon model of light will be essentially essential as we explore the interaction of electromagnetic waves with matter. Yeah, this is some like energy of some atomic and molecular processes. Yeah, this is breaking a hydrogen bond between two water molecules. We need this energy, and this is the energy released in metabolizing one molecular of ATP. Is this one. And breaking the bond between atoms in a water is this one. And like ionizing hydrogen atom in this energy. Yeah. So this is some common energy needed by some automatic and molecular processes. Okay. Yeah, this is what we talk about in today's class. Yeah, in today's class, we talk about the the Faraday's law. Yeah, the Faraday's law is just like help us to find the induced EMF and like after you find the induced EMF and then you can find the induced you use the Ohm's law to calculate the induced current, and then for the direction you can use Lenz's law. Yeah, and then we talk about the electromagnetic waves. yeah, we know some like features and properties of electromagnetic waves, and then we also learn the Maslow's law to how to calculate the intensity of electromagnetic waves, and also we learn how to calculate like each photon, like the photon, we talk about the photon model of electromagnetic waves, and learn like how to calculate the energy for each photon, and some features about like the photon model of electromagnetic waves. This is what we learn in today's class. Yeah, let's do a summary. Yeah, you also can check these videos for like the for the electromagnetic induction. Yeah, let's let's do some summarize. Yeah, first let's talk about some general principles. Yeah, the first one is electromagnetic induction. Yeah, we know the two generate the electromagnetic induction. The magnetic flux is the most important thing. Yeah, the magnetic flux measures the amount of magnetic field passing through a surface. Yeah, we use this equation, and this is the area of the like a conductor, and this is the electric field, and this is the angle between the axis of the loop, the like a conductor, and the like a magnetic field. Yeah, and if this theta equals 0, which means the magnetic flux is maximum. Okay. And then we talk about like Lenz's law. Yeah, we use Lenz's law to find the current direction. Like the Lenz's law, like specifies that there is an induced current in a closed conducting loop. If the magnetic flux through the loop is changing, the direction of the induced current is such that the induced magnetic field opposites the change in flux. Yeah, like if this bar magnet like go down, which means the this loop should generate opposite like magnetic field. Yeah, and then you use the right hand. And the similar thing, if this bar magnet goes up, which means it will generate the same direction. Yeah, and then use this direction. So, and then you use the right hand rule to decide the like current direction. Does it make sense to you? Okay. Let me continue. Yeah, then we talk about in this class, we talk about the Faraday's law. Yeah, the Faraday's law specifies the magnitude of the induced EMF in a closed loop. Yeah, and we use like a magnetic flux changing and the time changing the difference. Yeah, and this is equation we can get the we can get the induced EMF. And if there is an internal coil, we can multiple N to get the like induced EMF. And then after we got the EMF, induced EMF, we can use like the Ohm's law to get the induced current. That makes sense to you. Okay, and then we talk about electromagnetic waves. Yeah, an electromagnetic wave is a self-sustaining oscillation of electric and magnetic fields. Yeah, actually, it includes two different fields, electric fields and magnetic fields. And the wave is a transverse wave with the magnetic field, electric field, magnetic field, and the wave speed, velocity, materially perpendicular. Yeah, those three just perpendicular with each other. And the wave propagates with speed. This one, yeah, we calculated and found it's same with the light like travels in vacuum. And the wavelength, frequency, and speed are related by this equation. And Then for the electromagnetic waves, the amplitudes of the fields are related by this equation. Like the amplitudes of electric fields divide the amplitude of like a magnetic field equal the like a light speed 3 multiple 10 8 power 8. Yeah. And then we talk about like in last class, yeah, here after those general important general principles, we'll also talk about some like important concepts. Yeah, like we talk about emotional EMS. Yeah, actually this is just like the induced EMF, like how this emotional EMF like generated. Yeah, the you can see the motion of a conductor through a magnetic field produces a force on the charges. Yeah, this is like a motion of conductor through and the separation of charges leads to an EMF. Yeah, that makes sense to you. And we can use this equation to calculate the motional EMF. This is the velocity of this conductor moves, and this is L, the conductor's length, and this is the magnetic field. Okay, and we also talk about the photon model in today's class. And the electromagnetic waves appear to be made of discrete units called photons. And the energy of a photon of frequency f, yeah, if the photon of frequency is f, and the energy of photon is this one, yeah, the energy is hf, like h is just a constant, yeah. And this photon view becomes increasingly important as the photon energy increases. Increases. Yeah, you can see like um, and then there are some applications we talk about. Yeah, the first one is a changing flux in a solid conductor creates eddy currents. You can see these eddy currents. Yeah, these currents are very useful for some applications. For example, the trains and some like vehicles. Yeah. And also we talk about the like polarization and the plan of electric field and of electromagnetic wave defines its polarization, and the intensity of polarized light transmitted through a polarizing filter is given by Malu's law. Yeah, this is the like Malu's law, and where theta is the angle between the electric field and the polarizing axis. Yeah, this is, for example, this is the electric field. This is like a polarizing axis, and this is electric field. Yeah, and this is the angle between that one, those two. Okay, yeah, this is what we talk about in today's class. Okay, yeah, and like for the chapter 25, we mainly focus on EM induction and EM. Sorry. Yeah, EM induction and EM waves. And you can see, like after this chapter, and you should understand the nature of electromagnetic induction and electromagnetic waves. Yeah, and hope you have already learned those two things. Yeah, we talk about a lot, and but in like the content in chapter 25 is less than the content in 20 like chapter 24. Yeah, so yeah, I hope you can spend some time on those things, and it will be help you to explain some applications in real world. Yeah, if you have any questions, and just let me know. And yeah, we will have the final exam on Friday. And also, I will give you one more like labs tomorrow. Not tomorrow, today. Yeah, and then you need to finish all the homework, all the tasks, and all the labs like before Saturday. Sorry, before this Sunday. Yeah, and if you have any questions, problems, just let me know. Text me, call me, like email me. Yeah. Any questions, any problems? Yeah, we can like talk about that. Yeah. Don't like keep things in your mind. Yeah. If you don't talk with me, I don't know. Yeah. So just talk with me. Okay. Yeah. This is our last class. Yeah. Even I I cannot see your face, but I can feel you are there. So, hope I can have the in-person classes with you guys like in other semesters. Yeah, we can talk about everything in person, and I think that will be better. Yeah. Okay. Any questions? Just let me know. Okay. Bye.